All right. So time complexity for a problem is, we said, easy to equate, even though it's a little bit maybe counterintuitive to say, what are we talking about? Probably the one. So all of these are expressed as polynomial time, worst case, right, or upper bound. Big O is an upper bound on the time. And so we can compare algorithms, we can compare solutions to problems based on whether they have the same big O upper bound to them. So that can be, that gives us at least an initial approximation of how good two algorithms are, how time efficient they are. In practice, what do you think could affect, if we're doing kind of, granted, this measure, the big O, is kind of a gross estimate, right? The mere fact, if you recall, we throw away coefficients and we throw away lower order terms from the time equation. So what we might, this is the time to solve, time to compute, right, is a function of some right, it could be, some of these are 0, right? So we don't necessarily have every term in here. Let's see, but right. All right, so it's some series of terms, and no matter what the big O notation, I think let's make sure we got straight why we're doing this, and how do you get to big O notation, and what's the justification of why that's a allowable, sensible thing to do, right? So the whole purpose of getting big O notation is we want to classify, we want to categorize algorithms into different groupings that would have very close to the same result as key point as n gets big. So the method is just discard the coefficients and keep only the highest degree of n. And I think we've looked at this a couple times. The justification is as n gets big, all these other terms wash out relative to the highest order of n over here. And so big O of big O of T of n is just x to the n. Oh, I screwed this up. I'm sorry. I messed up my n's. I was writing a general strike it from the record. What I was putting it into terms of x. I've got n right there. I should have been doing these are the powers. N is my number of elements. And this is my x and x plus 1. The okay, so sorry for the caught it right away. So we're talking about the polynomials in terms of n. So the whole point being whatever the highest degree or highest power of n is the one that we want to keep. And that's what I got my one thing to mind your P's and Q's, another thing to mind your N's and X's. To put them in the right place. Okay, the rest of it is correct. So just to keep the notation right, this is to prevent confusion. All right, so polynomial things, time complexities are still in the world of tractability. What if I have n to the 50th power? That sounds pretty bad, right? But it's still tractable in our definition. And we'll look at a couple of instances here to kind of put some reality on to that. We'll look at a try all the possibilities kind of problem. All right. So we're going to contrast that with exponential intractables and that does not mean not polynomial or non-polynomial, but non-deterministic. And this is almost exclusively practically the intractable problems. And those would include two to the n, n to the n, n factorial. Now these are crazy. I've tried to draw them on the board a few times, but I really didn't realize I wasn't doing justice to them, so I wanted to have a pulled out from the archives a graph showing just how crazy these numbers get. I'm going to share that on the. I share my screen on the meeting here. Let's see here. What's that? Let's see. Let's start with the table here. And share. Boom. That guy. There. All right, so here's it's out of a book called Algorithmics, which has a very popularized treatment of algorithms, evaluation, and difficult to solve intractable problems and such. So you can see. Yeah. So as you go across the top, you can see n going from 10 to 1,000. And I wanted to bring this up to stress the just how big the numbers are we're talking about, right? Is 1,000 a big number? Pretty big, but not compared to, when you think in terms of like web traffic at a website, right? They get millions of hits. Places like Amazon, especially this time of the year, that gets to be unimaginably large. Handling, having the capacity for the website to handle so many customers and the whole thing. You're talking much larger than 1,000, right? So they have to deal with they're not using algorithms that are in this range, right? I mean, it would be impossible for them to get anything done. But interestingly, looking at things like they just threw a coefficient on this because we've got the coefficient on there. That's not strictly how we would do big O notation, but just for comparison, if your function were just a multiplier times n, like 5n, then you can see obvious results from that. That doesn't go up very fast, right? I mean, that goes up in a nice, actually, it's a linear increase. And then we talked about the best possible sort that you can do. Theoretically, falls into n log n, which is what that second row is showing. And notice if for that n of 10, n log n is less than 5n, just in that one particular case, because the log of 10 is, or log 2 of 10 is, what, 3.3. But so you can see the desirability, right? N times log n is not all that terrible. It's rising, but not at a very crazy pace. Much better than n squared coming across here, right? A million, 7 digits here compared to like 10,000. N cubed is still, yeah, it's getting up there. That's pretty big number, right? As you get to 1,000, n squared versus n cubed. And now look at what happens. So everything above here is tractable. Even though it's getting big, what we're concerned about more is what's the shape of the function? Kind of how is it changing? What happens if you increment? If you want to kind of have a touchstone, think about. Yeah, this is getting, between here and here, this is getting to be a big number. But what if I add one or add a couple to n? What happens in that? If you're looking at a little window around some value of n, if it increases or decreases a little bit, what's the kind of shape of the curve doing at that point? And so you can see going up a little bit, 1,000 compared to 1,001 or 1,010, you're still going to be around a billion here. Now, we'll look at the curve, but that's not the case when you're in this half of the graph here, this lower part, where the intractable functions live. He stops counting digits over here because 623 digit, like 10 to the 622 or 23, 744. Yeah, those are beyond what we can even. All you can do is sort of look at the exponent and go, wow, that's a really big exponent. But look at what n is. It's like 1,000 and or even 100. N to the or n to the n for 100 is like 10 to the 200th. I don't remember what the there are all kinds of estimates trying to make sense out of unimaginably large numbers, but the estimated number of atoms in the universe is I think smaller than a 100-digit number or something like that. I mean, it's past anything you have to compare with, right? It's really, really big. So hopefully that kind of illustrates a little bit why we have this divide between the intractable and the tractable. And think about, just, on 2 to the n, increasing by 1, increasing n by 1 immediately doubles the size of your time. So what's happening, remember I said, if you look at a window around, say, a given n, what's the shape of the curve on that little space? You can vary n. So if you it kind of give you touchstones, ways to think about it. If you're on an n cubed kind of function and you had to go up by a few elements, you'd still, if you could make it work for this, then you could probably increase your N by a small amount and still have a working algorithm, if you want to put it in that sense. If you have an algorithm that takes this much, 2 to the N, and you finally get it to work for N number of values, increasing to N plus 1 will totally break the system, and you won't have a solution anymore, right? So a tiniest increment of N makes a further intractable problem. We said for a 2 to the N problem, if you happen to use the example, say you got your program working and it took an hour to run, and it's of this nature, it takes 2 to the N operations for some N. It doesn't matter what the N is. Let's say you get it to work. It takes 1 hour to run for N. You double the processing speed, and how long does it take to run for those same N items? 1 hour, double the speed. Now it takes you half an hour, right? But now what happens if I add 1 to N? Well, you're back to the hour again, and you just lost all the engineering, the whatever it took to double your processing speed, which we haven't done actually doubling it for a while, right? It's been creeping up, but we seem to be hitting physical limits at a molecular level of how much faster we can actually make electronics as we know them right now work with the current technology we have. So the idea, whatever what you want to understand, right, when we're dealing with intractable problems, a naive approach or a naive suggestion, someone might say, well, why should we worry about whether a problem is tractable or intractable today? Because we've got technology is always improving. We've got computers getting faster. Wait a little while, and the problem will go away because we'll just have faster computers. So that's a very naive approach because, right, as I just illustrated, doubling the processing speed, which is not easy. Certainly today, right? I mean, we're in the gigahertz range for CPUs for personal computers, and even maybe you could double that in a few years, but it won't solve the problem. The nature of and the key idea, I guess, is that the nature of the problem itself, if it's in this intractable class of problems, then there's nothing you can do from improving your computation speed. The other picture that helps illustrate this little graph. Okay, I like this because much better than my feeble attempts to show the linear and everything that I've got on the board and trying to squeeze in these guys. Notice what kind of a scale is this vertically? Yeah, it's a logarithmic vertical scale there. So what that does is it really puts these guys into perspective of how crazy fast they go up, right? What's the slope here? It's like easily gajillions, right? So what do we look at? The 5n. There's a nice, very flat kind of line coming across here at this stage. The n cubed looks really tame, right? And when you, this kind of gives the perspective to what the intractable really means and what it looks like. N to the fifth, you know, a little more slope to it on the log scale, but relative to these guys, this is 1.2 to the n. So it's looking pretty crazy. I guess we don't have we don't have factorial on here, but similarly, it's going to come up a little bit slower. I don't know if it falls between these, but the 2 to the n and the n to the n. Go up really fast. So what does a, let's see here, let me, done with my screen. Okay. So we I wanted to give an example of a something on the order of a factorial let's say we're going to talk about one of the places I think I mentioned in here. When is the time that you might want a problem that you present to the world to be a non-deterministic polynomial or an intractable problem? It's exactly in the world of cryptography and cybersecurity. So coming up with a password. Let's just use let's see. So how many possibilities does this present? How many unique 8-character passwords?
Number too large.
Maybe.
I think what we look was in factorial.
Yeah, it's a little bit right. So how many? If we only use the capital letters, how many different capital letters are there?
Right?
26 is good.
26.
24 is A minus. You have like what, 26 choices for the first character, and I said they're going to be unique within the password. So then you have what, 25?
Yeah.
Anybody with a calculator? 6. It's less than 26 factorial. 26 factorial would keep going down to all the way down to 1, right?
Oh.
That's 8. That's just
I see.
right. There's 8 choices. So after you pick the first, you have 26 to choose from, then 25 to 4.
You can't choose this. You can't have the same number of unique. Okay.
Yep.
6 points.
Right. So I'm actually making it smaller than. So I put an extra requirement on there to make it
6.3.
So if you knew that the parameters for this person's password were as I described it, potentially how many tries would you have to make?
That many.
Yeah. So you may hit it sooner, but worst case, right? We're kind of looking at how long could it potentially take. 6.3 times 10 to the 10. So how big of a number is that? Pretty big. How big is how many seconds are there in a year? We could.
I think it's like 30.
Yes. Good guess. Something like 3.1 times 10 to the 7th. So if you check 1,000 passwords, if you can try 1,000 per second, how long will it take you to crack this password?
2 years.
We'll call that a 2 times 10 to the 3rd, right? So I said 1,000. So that's how many. I just do it. So this is how many seconds you have. So this is how many operations. So it would take you. It should be 2 years. Where am I? Oh, because you're doing 1,000. If you're doing 1 a second, it would take you. 2,000 years. Right? Since you're doing 1,000 per second, it's going to take you 2 years. That's pretty good. What if you allow uppercase, lowercase? It gets better, right? It gets way better. Because now you have what, 52? Kind of, right? Less than 52 factorial, but 52 times 51 times 50, etc. for 8. What if you make it a 16-character password? Then, yeah, you're pretty far out there. So the what we call the brute force, right, exhaustive search approach to cracking a password is not very effective. Certainly not very efficient.
Do you know how many symbols there are on a keyboard?
I believe you probably do, and will share that.
I don't. Off the top of my head.
Yeah, there's uppercase, lowercase. That's 52 plus
Numbers.
all the. There's like a symbol on each of the
26 keys.
Okay.
That you could get to 255, right? I mean, if you use 1 byte ASCII codes, would give you up to or 256 if you include a 0 character. Different ones. So 256 factorial gets crazy big, right? Or even if you only take the first 8 terms for an 8-character password. So that's not really how people get into passwords, right? I mean, they always publish what's the most popular password, right? Somewhere. We'll put out, the QWERTY or ASDF, like GH or whatever, or password, or 1 2 3 4 5 6 7 8 9. So if you were trying to crack passwords, you'd probably do better instead of the exhaustive search to try the most popular passwords once through, right? There's probably you can probably try 100. Also, can you practically try well, with one computer, can you practically try 1,000 per second trying to log into somebody's account? Probably not. Most accounts are, I mean, they purposely, right, are slowing things down so you can't reasonably do that. You could potentially have multiple sources trying to hit on the same account with different sources, different computers maybe, but typically when you try to log in, it takes it a little while, and they are not averse to putting some time slowdown right on there so that the number of hits is reduced. So this would fall in. You're starting to get a factorial type shape to the curve. And so that's why some of the SPY movies and that have the hero get to the device to be broken into and pop their flash drive in there, and at the last second, within a very short period of time, are able to snag and decipher the important information and go merrily on their way. I suggested the way to make money is to sell that algorithm, or you basically solved the question. So here's an important conceptual issue. Your book presents it. I am taking great liberties with and you're responsible for what we're doing in class rather than the particulars of the chapters that I am. There we go. That I'm using as a basis for what we've been talking about in this whole time complexity. So just to kind of restate the path we've been walking down here is we started with the question of undecidable problems, right? The question of can you tell whether a program will stop on a given input? And we said throwing away the kind of fringe or edge cases of, here's an empty program that has a main it just has an open curly brace and a closed curly brace. Is that going to stop? Well, yeah, pretty much. I mean, if the compiler or interpreter is running correctly, it stops. Or if you have a print line, hello world in there, is that one going to stop? So you could come up with a scenario, right, where for a given program, can I tell whether this one particular program will stop on a given input? And if you sort of load it with a pre-planned program to be tested, then yes, you can tell whether that one particular program will stop. But we're talking about in the general case of can you write a program which will take another program as input and tell you whether that program will stop? And the answer is that's impossible in the general case. And that has lots of implications for the whole concept of, can you prove that a program is correct? Well, there's a branch of computer science that looks at logical arguments for does this program do the specified calculation that we expected it to. And you can do logical assertions on the state. At this point, this variable has to be this value, or it has to be this relationship to another variable. You can come up with proofs of correctness as a human being, but since you can't even tell whether the program will stop on a given input, except for very, like I said, narrowed, tiny cases, you might look for some subset of, is there a while true loop inside of this code or something like that? We can't solve it's called the halting problem. It's kind of a classic in the area of decidability, computability, that says you can't tell whether a program will stop on a given input. And then, so that's the undecidable problems. And then we talked about, there are some decidable ones, like all the early DFA, NFA stuff, PDA stuff. We can tell whether those will stop. And so there are decidable problems that we know will give us a yes or no answer and stop. There are undecidable problems that we can't get an answer to. And then there's this whole world of they are decidable, but they are not practically solvable because of the time element involved. And so that's where the intractable comes from. So there is a distinguishing, undecidable problems are not the same as NP type problems, right? Doesn't mean they're undecidable. It's sort of two completely different questions. It's can you solve it at all, decidable or undecidable? And if it's decidable, can you decide it in a reasonable length of time, in a tractable length of time? So this is probably a concept that computer scientists should, worthy of the name and the degree, should have at least seen and could make an intelligent statement about. If someone were asking you while you're sticking your diploma into the frame, what is that whole NP thing about, right? And it's a question of, is there any possibility that the non-deterministic polynomial problems might have some polynomial solution that we just haven't discovered yet.
Sure. Okay.
Well, yeah, these have the nature of try all the possibilities, sort of in their, the way they have to be solved at this point. We've not been able to prove either side. From a practical standpoint, we should probably assume the answer is no. Why would that be? Suppose you're at work and you have some kind of a problem and you're looking into it and you're going,
No,
wow,
I don't want.
well, you can't just say no at work. Hey, but you start looking at a problem, you're going, I don't see any way it looks like. We're going to have to look at every single possibility here. And, right, if we take away, this only gets worse, right? If we take away the unique part here, then what is it? Then instead of just decreasing, it's 26 times 26 is 26 to the n, where n is the number of characters password, which is even a bigger number than this, so way bigger. But when we look at something where it's like, the only ways I can look at this to come up with a solution is, trying all the possibilities, or something like we just have to keep trying. It's going to be the product 26 times to 26 to the n to the 8 power. Then what does assuming that NP is not equal to NP save you from? Yeah, exactly. So it makes no sense to try and, if you can recognize that this problem is, there's evidence of this problem is definitely pointing toward an exponential solution, then you're not, unless you're trying to, win a Nobel Prize in computing or something for proving this is true, it's going to be a waste of your time typically to try and get a nice polynomial solution to solve this, to solve that problem that looks like it's over here, and so you have to take other approaches, which would include coming up with heuristic or estimating approaches, trying to apply some AI, try to throw away unlikely cases. So some of the things you might try are estimating the answer versus getting the exact answer. Finding, which word I want to use? Plausible, acceptable versus optimal. Right? If all we can accept is the very best possibility, then we may have to do the whole calculation. If we can come up with an acceptable result, that may be good enough. Well, I mean, by definition, hopefully we can come up with, we don't care necessarily it's optimal as long as it's within some specification. Acceptable will be usable. And
just from an algorithmic. I guess it's a computation. So heuristics, anybody have a definition for, without Googling, for the idea of heuristics? What is a heuristic? Probably heard the term.
No.
No, just no. Oh, like virus detection using heuristics. Yeah, that's a common place I put. Right. So the heuristic part is educated guesses,
Okay.
doing approximations, estimates, making, I guess, let me
Well, now
throw
we're just
in.
making up the story.
Throw in a few. Yeah, these all fall under the how a heuristic approach would work, rather than having okay, we know how to compute this, we know how to just go through these steps and you get to the other end. An algorithm is kind of I don't know, I guess we throw away we throw around the idea of a heuristic algorithm, something like that. But I think there's kind of a dichotomy. Algorithm intends a specific set of steps that will take you to the solution, right? Versus a heuristic, which hopefully is going to move you closer to the solution by looking at probabilistic. That's why when they apply it to virus detection, what does it look for? It looks for things, markers like if it's an executable program, it might reference certain operating system calls, APIs that could damage that could lead to getting access to parts of the computer that you don't want the program to get at. Looking at from taking statistical data on other identified viruses, looking for patterns of bytes within the executable file to say that it looks a lot like it has patterns of bytes in it that match something else. I got to deal with that on actually I do some occasional custom programming for a couple of customers, and tried to upload my nice little executable that I had created that contained no viruses. Put it onto Dropbox, and when the customer was trying to download it, gave them warning. This is and it may have been just that it did not come from the Apple Store, the Google Store. That maybe it just flagged everything, but finally had to. And if I renamed it inside of Dropbox to like .txt, it still gave the problem. So I had to rename .text, then upload it to Dropbox, and then
it was downloadable to the customer. But anyway, so heuristics do not always get it perfectly right. But you probably want them to err, from a practical standpoint, you probably want them to err to the side of safety, and make the developer rename their program first, rather than just let anything come flying down into the computer. And let's see, and one more. So I think we mentioned previously, NP complete problems are those which have been determined that if you can find a solution, if you could find a polynomial solution to any NP complete problem, then you would have basically proven that they are equal, because is a say it this way. So the whole idea of they are reducible to each other, which means if I can solve one of them, I can solve any of the other NP problems by essentially using, if I find a solution to one problem, I can use it as a subroutine to one of the other NP complete problems. And what we're saying is that they embody the essential problem, I guess, of an intractable problem to be solved. And so if you can solve any one of them, you can solve all of them. And that would then mean, because NP complete problems are representative of all the NP class problems, let's say solve any one in polynomial time, then you can solve them all. And therefore, what are the implications if P is, if you can actually solve, page 298 kind of voices the, shows the picture, either P and NP are really, although they do not appear to be, they're really the same class of problems, which means all the NP problems could be reduced to polynomial time solutions, right? Or the polynomial problems are a subset of all the problems that exist. P being a subset, but they're all really, or either P is a subset of NP, as in the easy to solve problems versus the intractable problems, or they're both the same and really we've just over decades not yet solved, not yet found the way to solve those NP problems yet. I think that about
finishes off my material that I plan to cover. So we'll do, review will be on Wednesday. And it'll be won't be any new material. This is stuff that comes up particularly, I think, on the last few lines of the review sheet that exists right now. And we'll do that as long as you have questions or things to be clarified, and answer questions about the exam. So that's about it. So we will stop recording here.